Hello, good morning, students. This is Dr. Sunil Kumar, Assistant Professor, Department of Chemistry, L&T College, Muzaffarpur. Welcome back to Coordination Chemistry. So today our lecture is focused on ligands, that is a special type of ligands called ambidentate ligand. What is ambidentate ligand? Here I will enlist some ambidentate ligands and how the chemistry is involved through metal ligand bond formation will try to illuminate you all. Okay, so as you know, the Werner's theory has a very diverse effect on the coordination chemistry. So because of the uh, production of the different coordination compound, okay, so that have actually real world applications. So now our topic is ambidentate ligand. Ambidentate ligand. Ambidentate ligand means ligands having two donor sites, right? As you know that ligand is a species having donor sites. So that can capture a metal or that can bind a metal to form a dative bond, and ultimately a complex compound is called ligand. So as you know that once M, that is metal, in a particular oxidation state, that is N plus, will react with a ligand, it forms a particular coordination sphere, that is Ml. If there is a octahedral atmosphere, right? So this is N plus. So coordination chemistry is nothing but Lewis acid and Lewis base reactions. Okay, so Lewis acid has a tendency to accept a pair of electron, while Lewis base has a tendency to donate a pair of electrons. So result in the formation of dative bond or coordinate covalent bond. So here we have actually taken a metal ion in a particular oxidation state that forms complexes with this ligand L. So this ligand has donor sites, right? So donor sites means it can donate a pair of electron, right? So pair of electrons. So if you have a metal M N plus, so that is electron deficient species, we call it as Lewis acid, right? Lewis acid. So it is electron deficient. So they have proper and suitable vacant orbitals to accept the pair of electrons from the ligand. Okay, so this may be either hard or soft, right? Soft acid, soft Lewis acid. This is hard Lewis acid. So in the coordination chemistry, actually, what preferences is that hard metal react with hard donor and soft metal react with soft donors. It means hard Lewis acid will react with hard ligand and soft Lewis acid will react with soft Lewis ligand. So ultimately the reaction between Lewis acid, that is electron deficient metal ion, with ligand is known as coordination reaction, and the coordination reaction is due to result of formation of the coordination sphere. So this is coordination sphere in the square bracket, and overall the charge N plus actually dictates that uh, how the this complex ion is stabilized by counter ion, right? So counter ion, in the previous lecture I have also discussed that it may be counter cation or it may be counter anion. So here Ml6, right? So N plus, so here complex is cationic. So complex is cationic means there is a counter anions. So there may be Xn minus, right? So there is a counter anion, right? So if complex is anionic, it means suppose we have Ml6, that is N minus, then here in the left side of the square bracket there will be N plus. So here counter cation N plus will stabilize this complex anion Ml6 N minus. Here Ml6 N plus complex cation will be stabilized by Xn minus, that is counter anion. So there is a choice, either the formation of complex cation or complex anion. So accordingly counter ion will stabilize the structure. So this coordination sphere may be either homoleptic or heteroleptic. Homoleptic means there will be all 6 ligands may be either same, or there may be different atmosphere or different environment in this system. Suppose we have Ml6N plus, so it may be Mx4Y2, right, N plus. This Ml6 means here all 6 ligands are same, so that are directly bonded to this metal cation, right? So they are homoleptic coordination sphere. So it has homoleptic coordination sphere, homoleptic coordination sphere, coordination sphere. Or either there may be chances that there may be different type of ligand in the coordination sphere, so that are directly bonded to this metal cation. So for example, there is metal, here 4 ligands are same and 2 ligands are same but different. So in this coordination sphere actually 2 type of ligand, that is X type and Y type. So X type ligands are actually total 4 and Y type ligand total 2. So overall 4, 2 and is 6. It means this is also octahedral geometry. So this has octahedral geometry, octahedral, and it has also octahedral geometry, octahedral geometry. But the coordination sphere actually decides that the physical and chemical property of the resultant complex compound. So it has different physical and chemical property, and it has also different physical and chemical property. So it is the ligand that decides the physical and chemical property of the ultimate metal complex. So ligands are actually important to create diverse class of compounds on a particular oxidation state of the metal or Lewis acids. Okay, so how the ligands actually affects the coordination chemistry, or you can simply say the manufacturing of the coordination compounds in the realm of the coordination chemistry. So that I will try to illuminate with a particular kind of ligands, that is ambidentate ligand. So ambidentate ligands means, so suppose we have XY type of chemical species, right? So if this is anionic, so XY minus, right? So they have, or this kind of particular ligands have actually either choice. So either it can bind with this side, or either it can bind with this side with a particular metal or particular Lewis acid. So they have a choice. So this is called actually ambidentate ligands. But at a time only one side can capture the metal. Okay, so the beauty of this ambidentate ligand, that is XY minus, so it this kind of ligand has choice, either it can bind with XY, right, XY minus, or it can bind with YX minus. So this kind of ligand has tendency to create two different metal complex, right? So both have different physical and chemical property. Physical chemical property means there may be different boiling point, freezing point, or refractive index, or you can simply say um, optical property like color. So it has different color, okay, but ultimately chemical composition of the complex is same. So this is also mxy and this is also yx. Chemical composition are same, right? So this is very important ligand in the coordination chemistry, that is ambidentate ligand. Ambidentate ligand, so they have two uh, different donor site, right? So they have a choice. So either this end will capture the metal or this end will capture the metal, and accordingly we can create the coordination compound, right? So better is that we have a various examples of ambidentate ligands that show diverse chemistry in the coordination chemistry. We'll try to elaborate. So we have a examples. So this is nitrite, right? NO2 minus. So what is NO2 minus? So this is NO2 minus means it is, you can simply say this is a anionic ligand, right? What is this? Is anionic ligand. So it has two type of actually element, that is nitrogen and oxygen. So you can simply say this is NO2 minus, right? So this is a type of ambidentate ligand because of presence of two donor sites. So this kind of actually ligand has tendency to form complexes with either nitrogen site or oxygen site. It means if we have a metal in a particular oxidation state and plus, they can form a dative bond with NO2 minus, or it has a choice, or it can form O and O, right? So negative ions in both case they are fixed. So what is the structure of this kind of ligand? That is NO minus and this is O. So this is negative side, negative oxygen ion. So this is electron rich species, so they can donate, right? So Mn plus, okay. So this type of variation in the ligand atmosphere actually affects the coordination chemistry, and they have also the choice that M N plus, so this is N and this is O, this is O, O and this is O negative. So because of presence of a pair of electrons, that is called lone pairs, so this lone pair also can bind this metal cation, right? So the beauty or the structure of or chemical composition of the complex is same. So this complex or this complex, you can simply say this is M N plus O N O minus. So chemical composition of this compound and this compound is same, but the chemical and physical property of both compounds will be different, right? So this type of variation in the coordination is structure actually decides that the property. So NO2 minus have a choice, either it can bind with nitrogen donor or oxygen donors. So this type of ligand is called ambidentate ligand. Another example is that is NCS minus, that is thiocyanate ion, NCS minus. So NCS minus, what is the structure? N double bond C double bond S, right? So this is negative charge. Okay, so this is the thiocyanate ion which acts as a ligand. It has two heterodonor sites. So one is nitrogen donor and another is sulfur donor. So this ligand can form a complex with metal in a particular oxidation state with N C double bond S, N minus, right? So Mn plus, here nitrogen acts as a donor site, and another possibility is that Mn plus, right? So S C, S minus C triple bond N, right? So here nitrogen anion, it acts as a donor site. Here sulfur anion acts as a donor site, but ultimately the structure and composition of the complex is same, right? But the property of the both complex will be different, right? So this is thiocyanate ion. So thiocyanate N donor, thiocyanate S donors. Okay, so both donor site can form complexes, different complexes, but the NCS minus at a particular time it will actually form either of the donor sites at a time. Okay, so one kind of complex either through nitrogen site or sulfur site may be obtained. Okay, so this is the second example of ambidentate ligand, that is NCS minus, and third one, that is CN minus, right? Cyanide ion, this is also anionic ligand. So this CN, C triple bond N, right? So this is your C minus. So this ligand also bears two type of donor sites. So because of presence of lone pair. So this is carbon donors and this is nitrogen donors. So in K4 FeCN6, right? K4 FeCN6, in this ligand, the iron metal cation, iron ion is directly attached with carbon. So beauty of this ligand is it may form complexes with like that, or it can form complexes with NC minus. So two different types of complex can be obtained through this particular ligand. So this is cyanide ion and it is called ambidentate ligand. And another example, lots of example, that is thiosulfate ion, S2O3 minus. So it has a choice, either it can form complexes with sulfur donor or it can form complexes with oxygen donor, right? So the structure of the ligand actually decides how different donors form complexes with metal cation, and it is also the nature of the metal cation or nature of the Lewis acid actually that form complexes with particular donor sites. Okay, so hard Lewis acid means hard metal cation will prefer hard ligand or hard donor sites, and soft Lewis acid, soft metal cation prefers actually soft ligand donor sites. So depending on the hard Lewis acid or hard Lewis base or ligands, the diverse variety of actually coordination compounds can be obtained. Here N3 minus, the most important ligand, that is azide ion N3 minus, which is union negatively charged ion N3 minus, and N3 minus, how it bonds? So N3 minus, right? N3 minus, this is azide ion. Okay, so this is also unidentate ligand, right? But this N and this is N, right? So this is actually the structure. Okay, N3 minus, and now this, and this is your, this is plus, and this is minus, and this is minus. So this is the structure, right? Ultimately this is a N3 minus. So here this actually forms complexes with either this is terminal and this is central nitrogen. So terminal and this is central, right? So during the stability of the this particular ion or during resonance stabilization, so this kind of anion has a tendency to form with either terminal nitrogen or with central nitrogen. So there will be two different types of coordination compounds. Okay, so this two different type of compounds actually have different properties and obviously applications. So this is azide ion is a very good example of ambidentate ligand, right? So another example, sulfite ion SO32 minus, SO32 minus, right? So this kind of particular ligand has also tendency to form complexes with either sulfur donor or oxygen donor, right? So it can form complexes with this side or through this oxygen donors. So this is also a better choice of ambidentate ligand, right? So that can form different coordination compound, right? So this is resonance stabilized, okay, and this is resonance stabilized. They can capture this metal through this fashion, or they can capture, so this is your sulfur and this is your sulfur, so they can capture with this type, right? So both oxygen can capture on a particular metal cation. Here both sulfur can capture this particular metal cation. So they have tendency to form these two different complexes. So they are very important class of actually organic ligand. So that is ambidentate ligand. Okay, so here I will give you one example that have different colors. Suppose we have a cobalt and this is NH3 whole 5 and another one ligand is NO2, right? So here 2 plus and another ligand CO NH3 whole 5, this is also NO2, right? Here 2 plus. But both these two structure are same, right? But here the bonding fashion of this cobalt and this NO2, this cobalt and this NO2 and this cobalt, this NO2 is different. Here cobalt bond O and O, right? Here nitrite to O, here nitrite to N, right? Here cobalt bonds NO, right? So minus. So here NO2 minus, in which nitrogen acts as a donor, or here NO2 minus, here oxygen acts as a donor center, right? So these two compounds are actually different. So this is yellow color and this is red color. So this is the beauty of the ambidentate ligand. So that can tailor the color of the compounds and of course the physical and chemical property of the compounds. So here 5-amine, here 5-amine, both are same. But here nitrogen donor, here oxygen donors, that differentiate or distinguish the compounds and its stability. Okay, so students, I hope that all of you have actually got the points what today actually I have selected like ambidentate ligands, and they are very important ligands in the coordination chemistry that actually have a choice to actually create different types of compound at a time. Okay, thank you so much.